The ground trembles. Not violently, not chaotically, but with rhythm. A low, deliberate percussion rolling through damp earth and root systems. Ferns quiver. Insects lift into the heavy Cretaceous air. Somewhere in the distance, a herd of horned dinosaurs stiffens, heads rising in unison. The forest is humid, dense, alive with the hum of a world untouched by mammals like us. Then it steps into view. 9 tons of muscle and bone moving with unsettling balance. A skull longer than a kitchen table, teeth the size of carving knives, eyes locked forward. Tyrannosaurus Rex. For more than a century, this is the image burned into our collective imagination. A scaly, roaring monster, a cold-blooded reptile, a sprinting executioner at the top of a savage food chain, the ultimate predator. But pause the scene, freeze the frame, because nearly everything in this picture, its posture, its speed, its skin, even its metabolism, has been quietly dismantled by science. What if it didn't sprint at highway speeds? What if it wasn't fully scaly? What if it wasn't even truly reptilian in the way we've always assumed? For over 100 years, we believed we understood Tyrannosaurus Rex. Museums mounted it, films immortalized it, textbooks simplified it. But fossil by fossil, scan by scan, that certainty has begun to fracture. The most famous dinosaur in Earth's history may also be the most misunderstood. And the real animal, buried beneath a century of assumption, may be far more extraordinary than the monster we imagined.
In 1905, inside the grand halls of the American Museum of Natural History in New York, a name was unveiled that would echo across the next century of science and culture: Tyrannosaurus Rex. The man who announced it, Henry Fairfield Osborn, chose the words carefully: Tyrannos, tyrant; saurus, lizard; rex, king. The tyrant lizard king. It was more than classification, it was branding. At the turn of the 20th century, paleontology was still young. Fossils were rare, fragmented, and often distorted by millions of years of geological pressure. When the first substantial T-Rex skeletons were unearthed from the Badlands of Montana's Hell Creek Formation, they were incomplete puzzles. Bones were crushed, some were missing entirely, others were reconstructed with plaster and educated guesswork. Scientists did what they could with the evidence they had, and they filled the gaps with analogy. The closest living relatives available for comparison, as far as anyone knew at the time, were reptiles, crocodiles, lizards, Komodo dragons. So Tyrannosaurus was imagined in their image, scaly, cold-blooded, and slow. Early museum mounts reflected this assumption. The skeleton was posed upright, almost vertical, its massive tail dragging along the ground like a tripod. The head pointed upward, jaws open in a frozen roar. The body looked heavy, cumbersome, imbalanced. It was an impressive spectacle. It was also biomechanically impossible. But that would not become clear for decades. The prevailing scientific belief of the early 1900s held that dinosaurs were evolutionary dead ends, oversized reptiles that had grown too large and too sluggish for a changing planet. They were thought to dwell in swamps, their enormous bodies supported by water. Their extinction was interpreted as inevitable, almost deserved. Evolution had simply replaced them with something more efficient. This narrative fit comfortably within the scientific thinking of the era. Reptiles were seen as primitive, mammals were advanced. Dinosaurs, being reptilian, were placed firmly on the primitive side of that divide. Tyrannosaurus Rex became the ultimate symbol of that worldview, a brutal but dim-witted predator ruling a world that was itself evolutionary inferior. And then culture amplified it. Throughout the early and mid-20th century, illustrated books and stop-motion films reinforced the image of T-Rex as a roaring, tail-dragging monster. By the time blockbuster cinema embraced dinosaurs, the archetype was fixed. In popular imagination, T-Rex was a scaly dragon from deep time, a living weapon powered by instinct alone. Museums displayed it that way, posters depicted it that way, children grew up drawing it that way. The image became fossilized long before the science was. But even as the public embraced the myth, subtle cracks were forming in the foundation. In the mid-1900s, paleontologists began to question the swamp-dwelling narrative. Sediment analysis of late Cretaceous formations suggested that many dinosaur fossils were found in ancient river plains and semi-arid environments, not deep marshes.
Trackways preserved in stone showed animals walking upright, tails elevated off the ground. There were no drag marks. If T-Rex had dragged its tail, the fossil record would show it. It didn't. By the 1960s and 1970s, a new generation of researchers began to challenge the slow, cold-blooded dinosaur model altogether. Among them was Robert T. Bakker, who argued that many dinosaurs were active, dynamic animals with elevated metabolisms. His ideas were controversial, even disruptive, but they ignited what would later be called the dinosaur renaissance. The shift was profound. If dinosaurs were active rather than sluggish, their entire biology had to be reconsidered. Posture, muscle distribution, growth rates, predator-prey dynamics, even brain size. And at the center of this reevaluation stood Tyrannosaurus Rex. The skeleton itself began to tell a different story. Its hips were structured for a horizontal posture. The tail, thick with muscle attachment points, appeared designed as a counterbalance, not a prop. The legs were long relative to body size, suggesting efficiency of movement rather than swamp-bound inertia. The skull, once imagined as a blunt instrument of terror, revealed intricate openings for air sacs and sinus cavities. The more carefully scientists examined the bones, the less they resembled a giant lizard. And yet the myth persisted. Why? Because the original narrative was simple, visceral, intuitive. A giant reptilian monster ruling a savage world is easy to grasp. It fits our archetypes of dragons and beasts. It satisfies our appetite for spectacle. But science rarely rewards simplicity. As analytical tools improved from bone histology to biomechanical modeling, assumptions were tested against physics, chemistry, and evolutionary theory, and those tests produced uncomfortable results. The upright stance, unstable. The tail-dragging pose, inconsistent with trackway evidence. The cold-bloated metabolism, difficult to reconcile with growth rates observed in bone microstructure. The solitary mindless killer, an oversimplification of complex ecological systems. One by one, pillars of the traditional image began to fall. But this wasn't a story of scientific failure. It was a story of scientific limitation. Early paleontologists worked without CT scanners, without computer simulations, without isotopic geochemistry. They reconstructed a prehistoric animal using chisels, plaster, and the closest living analogs they could find. They were not wrong because they were careless. They were wrong because evidence accumulates slowly. And Tyrannosaurus Rex, more than any other dinosaur, suffered from its own fame. The moment it was maimed, it became an icon, and icons resist revision. By the late 1900s, a paradox had emerged. The most studied dinosaur in history was also one of the most misrepresented. The more data scientists gathered from new fossils in the Hell Creek Formation to comparative studies of theropod anatomy, the clearer it became that Tyrannosaurus Rex didn't fit neatly into the category of giant reptile. Something about it was different. Its bone structure hinted at high activity levels, its growth patterns suggested rapid development, its posture contradicted earlier reconstructions, its evolutionary relationships began pointing towards an unexpected lineage. The tyrant lizard king was starting to look less like a lizard. The myth had been powerful. It shaped textbooks, museum halls, and blockbuster films. It defined an era of paleontology. But beneath that myth lay an animal far more complex, one that would force scientists to reconsider not just T-Rex itself, but the very nature of dinosaurs. And as the 20th century gave way to the 21st, new technologies would expose just how deep the misunderstanding ran. The monster we thought we knew was beginning to dissolve. What emerged in its place would be stranger, more nuanced, and far more revealing about life on Earth than the roaring caricature of the past.
The skeleton does not lie. It may be incomplete, it may be fractured, but under careful analysis, bone preserves truth with remarkable fidelity. And when paleontologists began examining Tyrannosaurus Rex with 21st century tools instead of 19th century assumptions, the corrections came quickly. The first myth to fall was speed. For decades, T-Rex had been imagined as a high-velocity pursuit predator, sprinting at highway speeds, closing in on prey with terrifying acceleration. Early biomechanical estimates in the 1990s proposed speeds exceeding 40 miles per hour. It was an exciting image. It was also incompatible with physics. Using advanced musculoskeletal modeling, researchers began reconstructing the animal digitally. Muscle attachment sites on fossilized bones were mapped, joint ranges of motion were calculated, body mass was estimated using volumetric modeling. In 2017, a detailed study published in PeerJ applied multi-body dynamic analysis to simulate how T-Rex would actually move. The results were sobering. An animal weighing between 8 and 9 metric tons could not safely run at extreme speeds without catastrophic skeletal stress. The forces transmitted through its femur and tibia would exceed safe mechanical thresholds. A misstep at 40 miles per hour would have been fatal. Revised estimates now place its top speed somewhere between 12 and 20 miles per hour. Still formidable, faster than most humans, likely fast enough to overtake injured or slower prey, but not a cheetah. Yet this correction did not diminish the animal's power, it reframed it. Detailed measurements of limb proportions revealed something subtle but significant. Compared to other giant theropods like Giganotosaurus, T-Rex had proportionately longer lower legs. Research from institutions including the University of Michigan suggests these proportions may have reduced the energetic cost of walking. In simple terms, T-Rex was built for efficiency. Long legs increase stride length and reduce metabolic expenditure over distance. Rather than a sprinter, it may have been an endurance walker,
capable of traversing vast floodplains while conserving energy. This makes ecological sense. Late Cretaceous North America was not a densely packed savanna of prey. It was a dynamic environment shaped by rivers, forests, and seasonal shifts. Covering territory efficiently would have been more valuable than explosive speed. The predator image shifted again. Then came the bite. If speed was revised downward, bite force moved in the opposite direction. Using finite element analysis, the same computational technique engineers use to test aircraft structures, scientists reconstructed the stress distribution across a digital T-Rex skull. The findings were extraordinary. In 2012, researchers estimated a bite force exceeding 8,000 pounds. Later refinements pushed that number above 12,000 pounds of force. No terrestrial animal in Earth's history is known to have exceeded it. But the real revelation was not just force, it was function. Unlike the serrated blade-like teeth of some theropods designed for slicing flesh, T-Rex teeth were thick, conical, and reinforced. Cross-sectional studies show structural adaptations for resisting bending and torsion. These teeth were not optimized merely for cutting. They were built for crushing. Fossilized bones of Triceratops and Edmontorosaurus bear puncture marks and fracture patterns that match T-Rex dentition. Some bones show spiral fractures, the kind that occur when fresh bone is twisted under force. Others show deep circular punctures penetrating centimeters into dense bone. This was not delicate feeding. This was bone processing. Such feeding behavior suggests that T-Rex exploited entire carcasses, accessing marrow and nutrients unavailable to predators limited to flesh. In ecosystems where resources fluctuate, that capacity would be a decisive advantage. The old debate, predator or scavenger, becomes less binary under this light. With its immense bite force and advanced sensory systems, T-Rex likely did both. It could kill when the opportunity arose. It could also dominate carcasses through sheer mechanical superiority. The monster narrative gives way to ecological strategy. But perhaps the most transformative correction lies not in movement or feeding, but in metabolism. For much of the 20th century, dinosaurs were assumed to be ectothermic, cold-blooded, like modern reptiles. Their body temperatures would fluctuate with environmental conditions. This assumption reinforced the image of sluggishness. Then paleontologists began slicing bones. Bone histology, the microscopic analysis of fossil bone tissue, revealed growth rings similar to those in trees. In T-Rex specimens, these rings told a dramatic story. Juveniles grew slowly at first, then entered explosive adolescent growth spurts. Some individuals gained over 1,500 pounds per year during peak growth phases. Such rapid growth is difficult to reconcile with a purely reptilian metabolism. Further evidence emerged from isotopic analysis. By measuring oxygen isotopes preserved in fossilized bone and tooth enamel, researchers could estimate body temperature regulation. Studies published in journals such as Nature suggest that large theropods maintain relatively stable internal temperatures, not identical to modern mammals, not identical to modern reptiles. Something intermediate, a metabolic strategy sometimes described as mesothermy, capable of generating significant internal heat but not fully endothermic in the mammalian sense. If correct, this places T-Rex in a physiological category unlike any major living animal group today. And then there is the most visually disruptive correction of all: feathers. In the 1990s, fossil discoveries from Liaoning province in China revealed exquisitely preserved small theropods covered in filamentous structures, protofeathers. Many belong to the same broader evolutionary clade as Tyrannosaurus. The evolutionary link between non-avian theropods and birds became undeniable. Shared skeletal features, hollow bones, furcula, wishbones, three-fingered hands, aligned in detail. In 2005, medullary bone tissue was identified in a T-Rex femur, a type of bone previously known only in egg-laying birds. The implications were profound. T-Rex was not merely related to birds, it was part of the lineage that gave rise to them. Direct skin impressions from some T-Rex specimens show patches of scales, particularly on the tail and torso. No fossil has yet definitively preserved a fully feathered adult T-Rex, but evolutionary context suggests a more nuanced picture. Juveniles, smaller and more vulnerable to heat loss, may have possessed insulating feather coverings. Adults with enormous mass and heat retention may have reduced or lost much of that covering. The tyrant Rex king may have worn plumage, at least during part of its life. The scaly dragon image fractures once more. Finally, the brain. CT scans of T-Rex skulls allow researchers to reconstruct endocasts, internal molds approximating brain shape and size. These revealed enlarged olfactory bulbs, suggesting an exceptional sense of smell. The optic lobes indicate strong visual processing capabilities, and the forward-facing eye sockets provided binocular vision and depth perception. Its inner ear anatomy suggests sensitivity to low-frequency vibrations, useful for detecting distant movement. This was not a blunt instrument of violence. It was a sensory specialist, an organism finely tuned to its environment through millions of years of evolutionary refinement. By the time all these corrections are assembled, movement, bite mechanics, metabolism, integument, sensory systems, the cumulative effect is unmistakable. The traditional image of Tyrannosaurus Rex collapses under the weight of evidence. In its place stands something more complex, a dynamic, metabolically sophisticated, evolutionarily advanced theropod, closer to birds than to lizards, built for efficiency rather than reckless speed, equipped with the most powerful bite ever recorded on land. The monster was never inaccurate because it was too terrifying. It was inaccurate because it was too simple, and simplicity rarely survives scientific scrutiny.
It is easy, in hindsight, to point to outdated reconstructions of Tyrannosaurus Rex and ask, how could they have missed it? How could scientists have imagined an upright, tail-dragging reptile when the bones themselves suggest balance and motion? How did the image of a sluggish, cold-blooded brute persist for so long? But this is not a story about failure. It is a story about limits. When Henry Fairfield Osborn named Tyrannosaurus Rex in 1905, paleontology was operating with tools that would seem primitive today. Fossils were extracted with hand tools, bones were reconstructed manually. There were no CT scanners to peer inside skull cavities, no computer simulations to model muscle forces, no isotopic chemistry to infer metabolic rates. Scientists had fragments, and fragments demand interpretation. To reconstruct an extinct organism, paleontologists rely on comparative anatomy, studying living animals to fill in gaps. At the time, the closest visible analogs to dinosaurs were reptiles, crocodiles, lizards, snakes. Birds were not yet widely accepted as dinosaur descendants. The evolutionary connection, though proposed in the 19th century, had not been fully embraced. So Tyrannosaurus was interpreted through a reptilian lens. It seemed logical. Reptiles were cold-blooded, therefore dinosaurs must have been cold-blooded. Reptiles sprawl, therefore dinosaurs must have moved inefficiently. Reptiles grow slowly, therefore giant dinosaurs must have lived slow, plodding lives. Each assumption reinforced the next. And once a scientific model takes root, it shapes future interpretation. Early museum mounts displayed T-Rex upright, tail dragging, jaws open in perpetual aggression. Visitors internalized that image. Artists reproduced it. Textbooks simplified it. The feedback loop began. Scientific uncertainty became visual certainty. Then came culture. Cinema magnified the image beyond academic halls. From early stop-motion animation to late 20th century blockbusters, T-Rex became an icon of terror. Its roar, a sound we invented, became inseparable from its identity. Its scaly hide and thunderous sprint etched themselves into global imagination. Once an image becomes iconic, revising it feels almost like betrayal. When paleontologists in the 1970s and 1980s began proposing more active, dynamic dinosaurs, part of what became known as the dinosaur renaissance, the resistance was not only scientific, it was psychological. The public loved the monster. Even some researchers were cautious. Extraordinary claims require extraordinary evidence, suggesting that dinosaurs were metabolically active, possibly warm-blooded, and evolutionarily linked to birds challenged deeply rooted classifications. But evidence accumulated. Fossil trackways without tail drags, bone histology revealing rapid growth, comparative anatomy linking theropods to birds, discoveries of feathered dinosaurs in China that blurred the line between reptile and bird. Each discovery required a revision, and revision is uncomfortable. There is also a structural reason we got it wrong. The fossil record itself is incomplete. Fossilization is rare. Soft tissues almost never preserve. Behavior does not fossilize directly. Paleontology is a science of inference, built on patterns extracted from fragmentary remains. In the early 20th century, only a handful of reasonably complete T-Rex specimens existed. Today, dozens have been studied in detail, including remarkably preserved individuals such as Sue, displayed at Field Museum. Each new specimen adds resolution, like increasing the pixel count on an ancient image. What once looked like a crude silhouette becomes anatomically precise. There is another factor, one rarely discussed. Narratives are powerful. The idea of dinosaurs as evolutionary failures neatly supported a broader story of mammalian superiority. Mammals were warm-blooded, intelligent, adaptable. Reptiles were primitive, bound to environmental temperature. Placing dinosaurs firmly in the reptile category reinforced a linear narrative of progress. But evolution is not a ladder. It is a branching tree. When researchers began demonstrating that birds are living descendants of theropod dinosaurs, the old hierarchy destabilized. If a sparrow is technically a dinosaur, then dinosaurs were not evolutionary dead ends. They were ancestors of a lineage that thrives today. That realization required reframing not just T-Rex, but the entire Mesozoic era. And reframing takes time. Science advances not in a single dramatic correction, but in increments. A paper on bone microstructure here, a CT scan study there, a biomechanical model challenging sprint speeds. Each correction might seem small in isolation. Together, they reconstruct an animal. But culture does not update incrementally. Images and textbooks linger. Museum displays require funding and redesign. Films prioritize spectacle over nuance. The iconic silhouette of T-Rex proved remarkably resilient. We did not misunderstand Tyrannosaurus because we were careless. We misunderstood it because science is provisional. Every reconstruction is a hypothesis shaped by available evidence. Early paleontologists were working at the edge of what their era allowed. They built a plausible model with limited data. As data expanded, the model had to change. And that change reveals something essential about the scientific process itself.
Certainty in science is always conditional. It is the best explanation given current evidence. When new evidence emerges, explanations adapt. The revision of T-Rex is not an embarrassment. It is a demonstration of methodological strength. The myth of the monster persisted for decades because it was simple, visually powerful, and built on the best knowledge of its time. The correction emerged because science kept asking harder questions. If the legs are built this way, how fast could it truly run? If growth rings show rapid development, what does that imply about metabolism? If closely related species have feathers, what does that mean for this lineage? Each question chipped away at assumption, and slowly the tyrant lizard king began to shed its myth. What remains is not smaller or less impressive. It is more complex. We did not just misunderstand a dinosaur. We witnessed how human imagination, technological limitation, cultural reinforcement, and scientific humility interact over time. Tyrannosaurus became a monster because monsters are easier to understand. It became something else when we allowed the evidence to speak louder than the legend. And in that transformation lies a deeper lesson, not only about prehistoric life, but about how knowledge evolves. The animal never changed. Our lens did.
Strip away the museum poses. Silence the cinematic roar. Remove the tail dragging in the mud. What remains is not diminished. It is refined. The real Tyrannosaurus Rex stands horizontally, its massive skull balanced by a thick, muscular tail acting as a dynamic counterweight. The spine runs nearly level with the ground. Each step is controlled, economical. The hips anchor immense leg muscles, built not for reckless sprinting, but for sustained, energy-efficient movement across wide floodplains. This is not a creature constantly charging. It is one that patrols. At roughly 9 tons, its body is a study in structural engineering. Hollow spaces within bones reduce weight without sacrificing strength, a trait shared with modern birds. Air sacs likely threaded through its respiratory system, improving oxygen exchange efficiency, another avian characteristic embedded deep in its lineage. The head, nearly 5 feet long, is not merely large, it is mechanically optimized. Thick nasal bones are fused, reinforcing the skull against extreme stress. When the jaws close, conical teeth, some over 8 inches long, do not slice delicately. They penetrate, they withstand torsion, they crush. The bite is not about theatrics, it is about dominance over resource. With a force exceeding any terrestrial predator known, Tyrannosaurus Rex could shatter bone, access marrow, and extract nutrients unavailable to less powerful carnivores. In ecosystems where survival depended on maximizing every opportunity, this capability mattered. But power alone does not define the animal. Its skull houses enlarged olfactory bulbs, suggesting an extraordinary sense of smell. Chemical traces carried on humid air would not go unnoticed. The forward-facing eyes provide overlapping visual fields, enabling depth perception, critical for judging distance during predatory strikes or territorial displays. The inner ear structure hints at sensitivity to low-frequency vibrations. The world of T-Rex was not silent, it was layered with subtle information, distant footsteps, shifting herds, the resonance of movement across terrain. This was an animal immersed in sensory awareness. Its growth patterns tell another story. Microscopic analysis of bone tissue reveals rapid adolescent expansion, explosive increases in mass during teenage years. Within 2 decades, a juvenile could transform into a multi-ton apex predator. Such growth requires metabolic capacity beyond what modern cold-blooded reptiles demonstrate. Tyrannosaurus Rex likely maintained a body temperature strategy distinct from any major living group today, not fully mammalian, not fully reptilian, but something uniquely dinosaurian. Large body mass would have helped retain heat, while active physiology supported high-energy behaviors. It was not a sluttish relic of a fading lineage, it was metabolically dynamic. And then there is the question of skin. Direct fossil impressions show scales across portions of the body, particularly along the tail and lower torso, yet evolutionary context complicates the image. Close relatives within the theropod lineage possessed filamentous protofeathers. Birds, the surviving descendants of that lineage, carry feathers as defining features. The most scientifically grounded reconstruction suggests a mosaic. Juveniles may have worn insulating feather coverings to regulate heat during early growth stages. Adults, massive and thermally stable, may have retained reduced feathering in specific regions, perhaps along the back or neck. Not a fully feathered bird, not a naked reptile. A complex integument shaped by age, environment, and evolutionary inheritance. Seen in this light, Tyrannosaurus Rex becomes less a caricature and more a system, a convergence of biomechanics, physiology, and ecological adaptation. It occupied the top tier of its ecosystem not merely because it was large, but because it was optimized. Energy-efficient locomotion allowed it to traverse territory without exhausting reserves. Bone-crushing dentition maximized caloric extraction. Advanced sensory structures enhanced environmental awareness. Rapid growth ensured that juveniles matured quickly in a competitive world.
Even its extinction reframes its identity. 66 million years ago, a massive asteroid impact near present-day Yucatan triggered environmental collapse. Dust and aerosols blocked sunlight, food chains destabilized, non-avian dinosaurs vanished. But the lineage did not end. Birds, the living descendants of theropod dinosaurs, survived and diversified. The structural traits seen in T-Rex bones, from air-filled cavities to specific joint configurations, persist in sparrows, hawks, and eagles. In evolutionary terms, Tyrannosaurus Rex was not an evolutionary experiment that failed. It was part of a lineage that continues. So what was the real Tyrannosaurus? It was not a dragon. It was not a cinematic villain. It was a highly specialized apex theropod, shaped by tens of millions of years of natural selection in late Cretaceous North America, an organism whose anatomy reflects physics, whose physiology reflects metabolic innovation, and whose evolutionary relationships blur the boundaries we once drew between reptiles and birds. The myth portrayed a monster ruling through brute force. The evidence reveals a creature ruling through biological precision. In correcting our image of Tyrannosaurus Rex, we do not make it smaller, we make it real. And reality, as it turns out, is far more extraordinary than the legend.
Return to the floodplain. The air is thick with moisture. Insects vibrate in the heat. A river cuts through wide, fern-covered lowlands under a late Cretaceous sky. In the distance, something moves. Not upright, not dragging its tail. Balanced, deliberate. A massive theropod steps forward, its weight distributed with mechanical precision. Its head tilts slightly, sampling the air. Muscles shift beneath skin that may bear scales in some regions, filamentous structures in others. Its eyes lock onto movement beyond the tree line. This is not the monster of early museum halls. It is not the roaring caricature of cinema. It is Tyrannosaurus Rex, reconstructed not by imagination, but by accumulated evidence. And that distinction matters, because the real story of T-Rex is not just about a dinosaur. It is about how knowledge evolves. In 1905, when Henry Fairfield Osborn introduced Tyrannosaurus Rex to the world, he worked with the best tools available: fragmentary fossils, comparative anatomy, careful reasoning. The reconstruction he and his contemporaries produced was not foolish, it was provisional. Science always is. Over the next century, new discoveries emerged from formations like Hell Creek. Technologies developed that Osborn could not have imagined. CT scanners revealing inner ear canals, computer simulations modeling muscle forces, isotopic analyses estimating internal temperatures. Each advancement sharpened the image, and each refinement required humility. The willingness to say, "We were mistaken." Not because the past changed, the animal remains what it always was, but because our understanding deepened. There is something profoundly human in that process. We crave certainty. We gravitate toward clean narratives. A giant reptilian monster ruling a savage world is simple. It fits our myths of dragons and beasts. It satisfies a desire for spectacle. But the universe rarely aligns itself with our appetite for simplicity. The deeper we look, whether at distant galaxies, microscopic cells, or ancient fossils, the more complexity we uncover. Systems replace caricatures, gradients replace binaries, nuance replace myth. Tyrannosaurus Rex is a case study in that transformation. It reminds us that science is not a static collection of facts engraved in stone. It is a method, a disciplined process of questioning, testing, revising. It advances not through certainty, but through correction. Every outdated reconstruction of T-Rex tells a story of what we once believed. Every modern reinterpretation tells a story of improved tools and broader evidence. The correction does not weaken science. It demonstrates its strength. And there is another lesson embedded in this fossil. Tyrannosaurus Rex once stood at the apex of its ecosystem. For millions of years, it thrived, an exquisitely adapted organism shaped by evolutionary pressures we are still deciphering. Then, in geological an instant, an asteroid impact altered Earth's climate and collapsed entire food webs. Dominance did not guarantee survival. Yet its lineage did not vanish completely. The evolutionary branch that produced T-Rex continues in modern birds, creatures that fill our skies, perch on our windowsills, and migrate across continents. The tyrant lizard king is not merely a relic of deep time. It is part of an ongoing biological story.
When we correct our image of T-Rex, we are also correcting our perspective on life itself. Evolution is not linear progress toward superiority. It is adaptation within context. Success depends on environment, timing, and contingency. And our interpretations are always limited by the evidence we possess at a given moment. Stand once more in that Cretaceous forest. Listen to the low tremor of approaching footsteps. The animal that emerges is not less terrifying because it is scientifically accurate. It is more impressive because it is real, an organism whose design reflects physics, chemistry, and deep evolutionary history. We once believed we understood it. We were wrong. And that realization is not a failure. It is the engine of discovery. Tyrannosaurus Rex did not change over the last century. Our lens did. And as that lens sharpens, as new fossils surface, as new technologies emerge, our picture of the past will continue to evolve. In that sense, the most powerful force in this story is not the bite of a Cretaceous predator. It is the human capacity to revise our own understanding. The tyrant lizard king still stands in museum halls around the world. But now, when we look up at its towering skeleton, we are not just seeing a prehistoric animal. We are seeing the history of inquiry itself. The gradual, humbling, extraordinary refinement of how we come to know the world.